Hi, and welcome to my presentation on ASLR in OPTI. I'm Jens Wiklander from Linaro Security Working Group. I'm also an OPTI maintainer. I've been involved in OPTI since the start of the project. Agenda. We'll start with a short introduction of what ASLR is, followed by what this means for OPTI core, which executes in privileged mode. With that done, we'll cover ASLR for trusted applications, or TAs. At the end of this presentation, we will have time for questions. What is ASLR? Address Space Layout Randomization is a security technique which involves randomly positioning different memory areas each time an application is loaded. This makes it harder to succeed with attacks which relies on knowing the address in memory of a certain component, for example, a function. If you have a buffer overrun that causes a returning function to jump to a different address, it's harder to exploit that if the address of a certain function isn't known in advance. So the main objective of ASLR is to make it harder to exploit a memory corruption vulnerability. ASLR is of course not a full protection against such attacks, but it makes it harder for them to succeed. In OPTI, we have two kinds of ASLR. One for TAs, which corresponds to what one may find in, for instance, Linux user space. The other is for OPTI core itself. This corresponds to, for instance, ASLR in the Linux kernel. We are avoiding to use the name kernel for OPTI core, since it would then be so easily confused with the Linux kernel. So we call both features ASLR, with TA or core added if needed. ASLR has been supported in OPTI since version 3.8. ASLR for OPTI core overview. The binary is still linked against the same address as the physical load address. The binary is also loaded at the same physical address as previously. The difference comes later when the virtual memory mapping is established. In the example here, based on QEMU, we have OPTI loaded at the usual physical address with MMU still off. Thus, some device also at the physical address defined in the emulator to illustrate how device mappings are assigned virtual addresses. If the MMU is enabled with ASLR disabled, we are keeping the same address for the memory we are executing from, but the device mapping is moved to use the next available virtual address. This makes better use of the virtual address space since we avoid having scattered mappings. With ASLR enabled, we get a completely different virtual memory map with nothing in common with the physical memory map. Depending on the address used for the device mappings may use an address just before or after the memory. This technique was used even before ASLR to allow loading OPTI into memory at very high or low addresses. A nice bonus for ASLR is that the useful address range is maximized. Random seed. The random seed is used to select a random base address. This seed is needed really early when initializing OPTI, so some platforms may not be able to produce this inside OPTI itself. Instead, we may need to rely on the bootloader to supply it. In case a device tree is provided to OPTI when booting, it could be provided in the node secure chosen from the property KASLR seed. This is analogous with how a seed for KASLR is provided to the Linux kernel. In OPTI, we have a default implementation in a weak function, get ASLR seed, to extract the seed from a device tree blob. In case a device tree blob isn't provided to OPTI, the default implementation returns 0 instead. This will disable ASLR for OPTI core, but it can still be useful for development. A platform can override the default implementation of get ASLR seed. For example, if the bootloader supplies the seed in a different platform-specific way, or if it's possible to use a simple driver to interact directly with some hardware device at this stage. With QEMU, it's the emulator itself which is providing KASLR seed in Secure Chosen. Building. The binary is compiled and linked as a position-independent binary to prepare for relocation. A well-behaving binary only has relative relocations, so we only need to accept that kind. Relocation entries have a generic format in order to support all kinds of relocations. Relative relocations are a special case, so a format tailored to this kind of relocations only can be more compact and easier to process. Compare using an array of ELF64 REL-A structs with a plain array of uint32s. In this case, we can reduce the size of the relocation data from around 18 kilobyte to 3 kilobyte. In case we are using the pager, we will still need most of the relocations even after the initial boot, so this saving is actually quite significant. We have a script that extracts the relocation entries from the ELF and converts them into an array of uint32s. This array is then appended to the T binary. This simplifies the assembly code involved when doing the relocation, since there will be no room for inconsistencies or unexpected kinds of relocation. Getting a build error while the script is converting the relocations is preferable over a runtime error during early boot, when even debug prints may not be available to help diagnosing the problem. Relocate. The binary is still linked against the load address. This is needed since we are starting to execute with MMU disabled, and we need C code to build the translation tables needed before the MMU can be enabled. Once the translation tables are built, we can relocate the binary and enable the MMU. Relocating the binary is just a matter of identifying each word in memory and increasing them with a load offset, where the offset is the new address to use minus the link address. The code doing the relocation is in principle as simple as the code shown here, but it's implemented in assembly instead to make sure that the code itself doesn't contain any address that may need to be relocated. Even if this C code would be safe with one compiler, another compiler may generate code with unexpected dependencies. So in this case, it's easier to implement the function in assembly, even if we must do it twice, once for 32-bit and once for 64-bit. Mappings. A mapping is created based on the seed. We are executing in the binary, so we need to keep a small part of the binary identity mapped. This is because the code enabling the MMU is executing from physical memory. The identity map is needed also after the primary CPU has enabled the MMU, since the secondary CPUs may needs to enable the MMU, also relying on identity mapped memory. Depending on how CPUs later are turned on, off, and on again, we may need to be able to enable the MMU after we have booted all CPUs. The identity mapped address range is usually quite small, only 1 or 2 pages. In this example, you can see that without ASLR, we normally have 2 ranges for mappings. One for memory to execute of the core from, and 1 range for devices. With ASLR enabled, we get 3 ranges. One for the identity map, which per definition is at the same address as the physical address. The other two ranges are kept next to each other, but anywhere in the virtual memory range. Possible locations. A virtual address is selected as a multiple of 4 kilobyte, as that is the smallest unit we can map. The entire virtual memory range can be used with a few exceptions, like the page at address 0 or overlapping the identity map. On a 4 gig virtual memory range, this gives almost 20 random bits. If a generated position cannot be used, a new position is generated instead of trying to shift the position slightly. This is needed because we would otherwise make certain addresses more likely. For example, at the beginning and the end of the virtual address range. We do want to make the used address as hard to guess or predict as possible. To generate a new position, we flip a couple of the most significant bits in the address. This should try another position that is different enough from the previous that it might work. After 3 failed positions, we will give up and run with ASLR disabled. But this shouldn't be very likely, since there are only 3 things that can conflict with the mappings: the beginning, the end, and the identity map. Translation tables, long descriptor format. Multiple CPUs can be active in OPTI at the same time, handling different TAs, so different CPUs must be able to use different memory mappings. But they also have to share the common mappings, like the OPTI OS code and data. This has led to this design with one level 1 table for each CPU. 1 or 2 of the level 1 entries points to finer-grained tables for the global mappings for the privileged mappings. With ASLR enabled, we often, depending on the seed, have 2 level 1 entries in use, with one taking care of the identity mapping and the other the rest of the privileged mappings. One of the unused level 1 entries is selected for user mappings. These mappings will be not global, that is, they are used together with a specific address space identifier, ASID, unique for each TA. Each TA will normally only be mapped in one CPU at a time, but the architecture would permit more than one CPU if that would ever be needed. Level 1 entries span 1 gig each, the level 2 entries 2 megs, and finally the level 3 entries maps each individual 4K page. In this example, the first level 1 entry is used for the identity map with a single entries in the corresponding level 2 table, which in turn points to a level 3 table with typically 1 or 2 entries, depending on the amount of needed identity mappings. The second level 1 entry, entry number 1, is used for the relocated privileged part of OPTI. These mappings are also global, since they are shared by all CPUs. The third entry is used for not global user mode mappings. This means that the first 2 entries in all the per CPU level 1 tables will have identical data. The third entry, entry number 2, will be changed as needed when different TAs are mapped on a particular CPU. TA loading. TAs has for historical reasons always been compiled and linked as position-independent executables. As you may recall from the previous slide, OptiCore selects a suitable virtual address range for TAs at boot time. TAs are linked against address 0 and are loaded with LDELF, the ELF loader in OPTI. LDELF relocates the TA to the address where it was loaded before being entered for the first time. So this process is a bit easier compared to OPTI core, which must relocate itself. LDELF is executing user mode 2, sharing the address space with the TA. So LDELF needs to relocate too. That's taken care of by the LDF startup code before the main routine is entered. LDELF could be compared with how LDSO works in Linux user space. ASLR for TAs. The size of the address range is limited by how many translation tables are available for user mode mappings. Translation tables are allocated to cover the lowest possible TA address to the highest mapped address. Translation tables are allocated for holes in the TA mappings too, so there's room for improvement. Address randomization is handled by LDELF with help from APIs provided by OPTI. The load address is randomized for each ELF being loaded, not only TAs or ELFs. There are dynamically loaded libraries and objects too. Thank you for listening. Now we have time for questions.